Hello, welcome again to the Future Internet course. We are now in the data plane programmability part of the course, and we already saw the motivation of data plane programmability, why it is important, and we actually saw briefly what are the main characteristics of data plane programmability. Now we are going to start with the P4 language. P4 language is actually the programming language to let's say program the switches in the data plane. So the agenda for today will be, for this video, will be a brief introduction to P4. We're going to see all the P4 language constructs. And then in the next video, we're going to have a real demonstration of, let's say, simple program with P4, in which we are going to use all the information that we will see here. The material comes from Jonathan Adilson Marquez and Luciano Pascual Gaspari from the Federal University of Rio Grande do Sul in Brazil. You have all these presentations also available in the course material. So what is P4? So P4 is this is very important. A domain-specific language is just for switches, and with P4 programs, you will be able to specify packet processing in the programmable switches. So how the packets are actually processed by the switch. This is the main feature of P4. So as we saw last class, and we're going to see more details here, a P4 program defines what are the headers that the switch should know. So what are the headers that the switch will recognize? For instance, Ethernet or VLANs or IPv4, or even custom headers, or even transport header like UDP or TCP. Then when should the switch parse each header? This is also important. How the switch should process packets according to the information gathered from the parse headers. So the when is what is, let's say, the sequence of processing. So first I maybe should process the Ethernet header, then what follows. So maybe VLAN headers or IPv4. So I can also program what is this sequence of headers processing. And then how the switch should process the packets is the match and action table. So what I will define is how to do a match, what are the possible match possibilities, and also what are the action possibilities. And then the match plus action will be something that will be defined as normally in SDN by the control plane. Okay, so as we saw last class, the queues and the scheduling is outside the scope of P4. This is configured at runtime. Okay, so as we also saw, what we have is something called a P4 file that we are going to define. The P4 file will be compiled by the P4 compiler. In the control plane, you will have a switch code and something called a P4 information. First, we will install an update in the switch code through the P4 runtime. So I will tell the switch, you will behave like this switch, you will recognize this type of headers, this type of matches, this type of actions. And then the second part is that the installation of forwarding rules, as we did with OpenFlow, we can do it again also with the P4 runtime. So we have one part where we tell the switch how to behave, or what is the headers that it will recognize, and so on. And then a second part, which is like the normal OpenFlow we had before, installing and querying forwarding rules in the data plane from the control plane. Okay. So in P4, we will have these constructs that are very important. First, the data declaration. In the data declaration, we have the protocol headers and the packet metadata. We have the parser programming, in which we will extract the information of the headers. And we have the packet flow programming, which is the best and very important, because here we define the tables, the actions, and the stateful and less objects. Okay. So let's see each of these constructs, which are the main ones in P4. So first one, let's see the data declaration. So here we will see the protocol headers and packet metadata. The protocol headers. So this is the way to define a header in P4. P4 is a language that is the syntax is very similar to C or C++. So we define something like a struct, which is a header with this header keyword, and then we put the name of the header. For instance, Ethernet. What that Ethernet header normally has: destination Ethernet address, source Ethernet address, and ether type. And we define how many bits each field has, right? So in IPv4, if you go to an IPv4 header, you can see all these different elements or fields like version, the internet length, the DSCP, the total length, counting with the options, the ID, the flags, the time to live, the protocol in the upper layer, so if it's TCP or UDP, the checksum, the source IP address and destination IP address, and also some options. And this is the length in terms of bits of each of these fields, right? So this is the way I define a header of IPv4. Each time I will parse a header of IPv4, I will be able to find all these fields. Same with TCP here, for example, and also same with this custom header. I can define just a header that I need for me, is custom, and I will say, okay, my switch will recognize this custom header, which is not a standard. It's called my header, which will has a destination field of 256 bits and a message field with the same 256 bits of length. So this is the way of declaring headers in P4. We will see this with more detail, of course, in the demonstration. We also have metadata, and the metadata, remember, that is all the possible data that you can know from a packet that it is outside the packet, the headers itself, right? So for instance, the ingress port, the physical port from which the packet actually input the switch, or the egress one, some egress specifications, and some other fields that are outside the headers of the packet, but are information of the packet. So this is the metadata. There is one standard metadata, or even metadata for queues, like the timestamp, or intrinsic metadata, so the ingress timestamp, where or when exactly the packet ingressed the switch, and with that you can calculate delays and so on, right? So there are a lot of metadata, and we're going to go in more detail also in the demonstration here. But the thing is that you can also declare with what are the metadata that your switch is going to be able to understand. Okay, so we had the data declaration, and then we have the parser. So in parser, what we have is the transitions, right? From parsing one header to the other one. So for instance, let's see this figure here in which we have the transitions of a normal switch parsing a header. First, it will parse the Ethernet headers. It will then know if the packet is an IPv4 or IPv6 packet, and it will then have the structure for IPv4 or 6, and then we can also parse the transport protocol and have some options from either UDP or TCP. So if we go to the code, first we make the start transition, in which we say, okay, which will be the first parse that we are going to do. And then the parse is Ethernet. In this state, I will say parse Ethernet, and I will extract the Ethernet header of the packet. And I will actually say here in the parser, okay, in the Ethernet ether type, inside the Ethernet header, in the ether type field, I will say if is this type, which is IPv4, please use the parse IPv4 state. If it's this one, which is IPv6, please use the parse IPv6 state. If it's default, maybe it's just a layer 2 packet, just accept the packet, okay? And then you have to define each state. So in parse IPv4, I will just maybe get or gather the length of the packet and saying, okay, verifying the length. If this length is greater than this or less than this, the header is not valid, right? And I can also make a transition saying, okay, I will go to the protocol field of the IPv4 header. And if the field is this one, then I am talking about UDP. So go to the state parse UDP. If it's this one, I go to the state TCP, parse TCP. So please go there. If it's default, just accept the paper. So in this way, you can define all the, let's say, logic sequence on how to actually parse the packets. And then, okay, you will get all the information of the parsing that you are doing. This is the second thing that you have to define in a P4 program. Then you go to I would say the most important part, which is the packet flow programming, which are the forwarding tables. So you will define the match and actions that are accepted in your P4 program or in your switch. So the most fundamental units of the processing pipeline are here. A P4 program defines at compile time for each table the following: what to match on, and the type of match. So what are the fields I will match on, and which match I will do. All a list of possible actions. So what are the actions that I can apply to the match, and additional attributes like, for instance, table size. This is at compile time. At runtime, each table will be populated or should be populated by the control plane with one or more entries, each with specific key to match on. So I will say, okay, you will match on this, and the specific action that will be carried out when there is a match, okay? And the primitive actions that you can have is mark packets to be dropped, modify fields of the packet, addition, subtraction, bitwise operations, add, remove, copy, push, and pop new headers. So you can do all of this in the headers, and apply match and action tables. You can also have compound actions, which are a little bit more complex. Is the composition and chaining of multiple primitive actions. Okay. So here we will see, this is a very simple example of packet flow programming in tables and actions. So what I would say, okay, if the IPv4 header is valid, I will apply this LPM, which is longest prefix match. Is one match that is very common in IP, which says, okay, depending on your IP address, you will match the longest prefix, well, the subnet that, of course, matches your address and has the, let's say, the biggest net mask. Okay. So I would say the key here will be the IPv4 destination address. So I will match on the destination address with longest prefix match. So for instance, the table will be something, I mean, in the end will be something like that. Okay, if destination address is from this network, the action is this one. If the match is from this other network, the action is this one. And you will put this to the egress specifications, which is metadata of the packet, okay? So possible actions for this that will be possible for this long prefix match in the IPv4 destination address are forward IPv4 packet or drop packet. And I will have, of course, to define the action. So the action forward IPv4 packet will just update the egress specification, the metadata, and will decrement by one, subtract by one the time to live of the IP packet, saying that, okay, you already passed here, so this is one hop that I will count, and therefore you have to decrement the TTL. And that's it. this is the action. Okay, the address specification is this one, so you will go to this port or this other port, and so on. This is a very also simple example. We're going to, in the demonstration, we're going to see some similar things in more detail. In packet flow programming, you have stateless and stateful objects. Header and metadata are always stateless, so it will not depend of the. I mean, the headers and metadata are just dependent on the packet, so they will be reinitialized for each packet. On the other hand, the stateful objects keep their state value across packets. Okay, so for instance, counters, meters, and registers are stateful and can be used in before. You can have counters in the switch, incremented with each packet to count packets, for instance, or count bytes or packet units, whatever you want to put. You can have registers to store arbitrary data in like a vector structure in the switch, depending on the packets that are arriving. And this is also stateful. It will be maintained in the switch. And meters that keep a bucket state, for instance, green, yellow, or red, also like to indicate some things. I don't know. The interface is very full, so the bucket state is red or is okay. Bucket state is green, and so on. With that, you can take decisions in the switch. So these stateful objects are also, this is a little bit more advanced, but we'll see some examples in the demonstrations. Okay. So with this, we will have the demonstration that I invite you to see in the next video. Thank you very much. And please watch the next video with the demonstration of a simple example in P4. Thank you.